Okay, we're going big here on this one. We're going to try and get through this entire section in one video under 20 minutes. Probably not possible. We'll give it a shot. Okay. Characteristic equation. Before we get to talking about the characteristic equation, we have a fun little side note about determinants and a new way that we can find the side note to find those things. This actually is based on what we already know about how to find the determinant using our row operations. So if you remember, if I do my row operations until I can get to a diagonal matrix, and by diagonal I mean triangular matrix. So if I do my row operations till I can get to a triangular matrix and I follow those row operations, I can use them to backtrack what my determinant might be. Now, one of those things, right? If we found that row replacements, that these guys had no impact. These didn't change our determinant, right? Row interchanges switch the signs. And that scaling scaled the whole thing, but what we're going to do is we're going to try and not use any scaling. So no scaling, just to get us down to a row reduced, and by row reduced, I mean just an echelon form of our matrix. And then to find that matrix, right, remember if I have a triangular matrix, the determinant of a triangular matrix is just the product of the diagonals. So here's a fun little proof. If the determinant of A is 0, or when it's not invertible, it's 0. That doesn't matter. It's just going to come out to be 0. If it is invertible, then if I can get down to a diagonal matrix, and the only thing I use is either row replacements and row interchanges, then I can take -1 raised to the power of the number of row interchanges. And the reason this works is, again, a row interchange switches the sign. So if I do 2 of them, it would switch the sign twice. So -1 squared is +1, which means that I've gone back to the original. And we don't have to worry about dealing with any row replacements. So here's an example. We're going to find this determinant. So right now we're not in a triangular matrix form. But if I can get this to triangular matrix and I can notice how many times I do any kind of row interchange, so just flipping, right? You switch U and U, then we can get there. So first thing I'm going to do is I'm going to do row 2 minus 2 row 1. That's going to give me 1, 5, 0, 0, -6, -1, 0, -2, 0. Now, I'm not quite at the place where I have a triangular matrix yet, so I still got to keep going. But this time I'm going to do row 2 replaced with 3 times row 3. So far I've not done anything that is going to actually change the value of my determinant. All I've done is some row replacements, and row replacements don't do squat, right? At least to our determinant. So 0, 0, -1, 0, -2, 0, and I'm so close to having a diagonal matrix, not a diagonal, triangular. All I need to do is switch these 2 rows. Now here's where we end up with a switch, which means that I have had 1 row interchange. So far, if I'm keeping track, so far R is equal to 1, right? So here's our first switch. And this switch gets us to a diagonal matrix, so I don't need to go any further. So it turns out that the determinant of this, of A, is going to be equal to -1 raised to our R power, which we found was 1, times the product along the determinant, or along the diagonal. So 1, -2, -1 is going to give me a whole whopping -2. Now, I didn't have to do my row operations in that order. And in fact, I don't even have to get down to that exact echelon form. So remember way back when we talked about how there's multiple echelon forms for any matrix. There's only one row echelon form. So echelon form, I just basically Basically, echelon form means make a diagonal, or make an upper triangular matrix. That's all echelon form is make a triangular matrix, where all of the lower ones are 0. The stuff in the uppers are numbers. All right. But I could, at this point, from there to there, I could instead use row 2 to eliminate the -2 in row 3. Right? So if I did row 3 minus 1/3 of row 2, that gets me the matrix 1, 5, 0, 0, -6, -1, 0, 0, 1/3. Right? And in this one, I've done no replacements. So this tells me that R equals 0. So my determinant here, just to show that it still works, would be my -1 to the 0, which is always 1, not 0. Just throw that one out there, times 1, -6 and 1/3. -6 times a third is -2. This is 1. This gives me my -2 again. Hey, party. Okay. So for those of you that I've, we'll call it chastised for trying to use that the determinant doesn't equal 0 to prove that something is not invertible, and I keep telling you it's not in the invertible matrix theorem. Well, what I meant was it wasn't in the invertible matrix theorem yet. Now it is. Yay! So we're adding to our invertible matrix theorem. So the next thing that we can add, and hopefully this should follow, that the number 0 is not an eigenvalue of A, right? We talked about this in the last section. If AX equals lambda x, if this is 0, that means that AX equals 0, and this implies that if A is invertible, then it says only the trivial solution. But in order for this to be true and be an eigenvalue, then that means that A has to be not invertible. So by saying, but 0 being an eigenvalue would mean that A is not invertible. So 0 not being an eigenvalue means that A is invertible, and we can keep going on with our lives about A being invertible. The last is that our determinant of A is not 0. So as long as determinant of A is anything other than 0, then it is invertible. And this came from the properties of determinants. So that also came from, listen, it's all you know, mashed up together, and yay. This guy, oh, I don't know what happened there. Ooh, whatever. This guy is important. Okay, our triangular matrix. If I can get down to a triangular matrix, then the determinant is the product of the entries on the diagonal. We love that guy. Right. So, our characteristic equation. All right, now we can come back to this idea of eigenvalues and eigenvectors. We were just taking a little detour about our determinants there. Fun fact, it was exciting. Hope you enjoyed it. All right, our invertible matrix theorem is like everything here. So we want to find the eigenvalues of A. So what we know so far is that we know this is true. So AX equals lambda x, right? Implies that these things here are eigenvalues. We've done some rearranging, and we've gotten down to A minus lambda I of x should equal our 0 vector, right? Now, we know that this is true, and that lambda is going to give us something as long as this has a non-trivial solution. All right, so this is a non-trivial solution to get our lambdas. Right? Now, if it only has the trivial solution, then lambda could be anything, and it doesn't matter anymore. We don't care. we want this for when that actually has a non-trivial solution. Now, from our lovely bit of coconuts over here, lovely bunch of coconuts, we know that if A is invertible, right, that the equation AX equals 0 has only the trivial solution when A is invertible. A is invertible, right? But we don't want the trivial solution. So therefore, that means that this thing needs to be non-invertible. And what we just added to our lovely bit of information down here, we just added that the determinant of A is not 0 if A is invertible. Therefore, the determinant of A minus alpha I needs to equal 0. So if it's not invertible, needs to equal 0, and then we can get our alphas. Was that fun? Did you enjoy that? I enjoyed it. So here we go. So we're going to find our eigenvalues of this vector. By vector, I mean double vector matrix. All right, so our eigenvalues. Here we go. We're going to find this first. Then we're going to find its determinant. And then we're going to set it equal to 0. And then we're going to solve for any alphas. And you're going to see something magical happen. And that is, we're going to get some numbers. So here we go. So A minus alpha I, or lambda I, we don't know what lambda is. We're trying to actually solve for that now, which means that we're going to end up with a matrix that has that stuff in it. So my A minus lambda I matrix is going to look like 2 minus lambda here, a 3, and negative 6 minus lambda. Remember, it's only the diagonals that are going to get this minus lambda thing, because, right? It has to do with this situation. We talked about it. Okay. 2 by 2. We love a 2 by 2. That means that the determinant of this thing, of A minus lambda I, is equal to the product on the diagonals. So that's 2 minus lambda, negative 6 minus lambda, minus 3 times 3. And this is an equation. Oh, look at that. And if I multiply this out, and please do. Now, I'm not testing your algebra skills. I don't care how you do this, but use something to simplify this. Use something to get you down to a polynomial here, whatever. But if you multiply this out, we find that the determinant of A minus lambda I is equal to lambda squared plus 4 lambda minus 21. And what we're going to do is we're going to set this equal to 0. So lambda squared plus 4 lambda minus 21. We're going to set it equal to 0 because if I set it equal to 0, that makes my matrix not invertible, which makes this possible. Yeah. All right. So we can factor this, or honestly, I don't care. You can go use a calculator, use Symbolab, use Desmos, use something to find the solutions to this equation. But I'm going to factor it real quick because this one's not bad. If I do lambda plus 7, lambda minus 3 would equal 0. So this tells me that my eigenvalues are either a negative 7 or a positive 3. And those are my eigenvalues. Sorry, my lambdas start to look a little funky over time. I feel like a backwards K that's just kind of sad. Okay, so that's it. And it turns out that what we get when we find the determinant and set it equal to 0, we call this the characteristic equation. So for this particular vector, this lambda squared minus 2 lambda minus 21 equals 0 is called the characteristic equation. Now you'll notice, and this here, in this case, A was a 2 by 2 vector, or 2 by 2 matrix. And I got a characteristic equation that was a polynomial, right? So the degree of our characteristic equation was 2. Oh, there might be something to that. I don't know. Coincidence here? Oh, and I got 2 lambdas. More 2s, more conspiracy 2s. That's not a conspiracy, right? Anytime you have a polynomial of any size, the degree tells you how many zeros that's going to have, right? And that's what we're solving for. We're solving for the zeros of this characteristic equation, or we're solving for the zeros of this polynomial. The part without the zero, if I just do the determinant of a minus lambda I, we call this the characteristic polynomial. And the characteristic polynomial has degree n, and therefore it has n eigenvalues. Now, there are times where some of those eigenvalues are not real. The only ones we're going to talk about here are when we have real number eigenvalues. And right, if you think about any degree polynomial is always going to have n zeros. Now, some of those zeros might be imaginary. Some of them might have multiple multiplicities, right? If you think about x squared, right? X squared looks like this. In this case, x equals 0 is the only solution, but it's x equals 0 with a multiplicity of 2. Now, I could shift x squared up and down. And every time I shift x squared up and down, if I shift it down, now I have 2 zeros. If I shift it up, I have no zeros. But this no zeros actually means that I have 2 not real zeros, or 2 imaginary zeros is what I was looking for. So same idea. So our characteristic equation is going to tell us how many of our scalars we're going to have, or our eigenvalues we're going to have. And it's great. It's beautiful. All right, let's find the characteristic equation and the eigenvalues of this matrix right here. Now, I hope you didn't panic. This is a 4x4 matrix, right? 4 by 4, which means I'm going to have a 4th degree polynomial, which means I'm going to have 4 eigenvalues, which means I need to define the determinant of a 4 by 4 matrix, which means I'm going to cry a little bit, except for the fact that this guy is triangular. Yay, triangular matrices. We love them. We love them. They make us very happy, right? So in this triangular matrix, all we need to do is find our A minus lambda I matrix and find the determinant of that. And the determinant of that is just us multiplying what's on the lovely diagonal. Or in other words, we don't really have to do anything. Like, we don't actually have to find the characteristic equation to find the eigenvalues in this, but we're gonna, just because it's gonna happen. All right, so I'd have 5 minus lambda, -2, 6, -1, 0, 3 minus lambda, -8, 0, 0, 0, 5 minus lambda, 4, 0, 0, 0, 1 minus lambda. And our characteristic equation is just going to come from the determinant of this thing, and the determinant of A minus lambda I is the product of the diagonals. So in this case, it's 5 minus lambda, 3 minus lambda, times another 5 minus lambda, and another 1 minus lambda. Now, because I don't have any constants, right? So up here, notice I had like some extra stuff going on here. So it wasn't just a product of those two things with lambdas in them. There was this extra -9, which is why I actually had to multiply this out. I had to just do my distribution here with these two terms and then combine any like terms to get me down to this actual equation here, this quadratic. In this case, in this case here, I don't actually need to multiply any of this out in order to get to the heart of or solve for the eigenvalues here, right? Because I don't have any additional like plus a 9 or plus a 6 or plus something else besides just these 4 products, then those 4 products are that's it, right? And that means that, so this would be our characteristic polynomial. And then the characteristic equation is what happens when we take that and set it equal to 0. So 0 equals that 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda. And the solutions to this tell us that either lambda equals 5, 3, 5, or 1. All right, so there's my 4 values. Now this tells us that I have the same value twice. So my eigenvalues are lambda 1 would be 5, and it's got a multiplicity of 2. Lambda 2, oh, that's not a lambda anymore, is 3, and lambda 3 was 1. Okay. Now, if you count up, I have, based on this, I have 1, 2, 3, 4 eigenvalues total, or 4 that satisfy a 4th degree polynomial, which satisfies a 4x4 matrix. Yeah, go get it. Okay. The next couple examples are not quite as bad. Well, okay, this wasn't bad. No. This guy, look at that. We don't even know what the matrix looks like, but we do know that I have this characteristic polynomial, and the eigenvalues is what happens when I set that thing equal to 0. Minus 4 lambda to the 5th, minus 12 lambda to the 4th. We're going to set it equal to 0. Hopefully your little factoring follicles are abuzz and excited. This one's a nice easy one to factor, right? I can take my lambda to the 4th out, so I get a lambda squared minus 4 lambda minus 12. Nope, no more lambdas. Took it out. Equals 0. And then I can factor this quadratic here into lambda minus 6 lambda plus 2, right? So my eigenvalues are not always going to be positive values. So far, they've been pretty, I mean, they could be anything, honestly. They can be anything, including not real numbers. We won't just talk about not real numbers eigenvalues here, but they do show up in other applications, in particular differential equations. Woo-hoo. Okay, here we go. This could equal 0. This, if that's 6, and if that is negative 2, all 3 of those will give me a 0, or will give me a true statement in this here. So our eigenvalues, my first eigenvalue is 0, and it has a multiplicity of 4. Right? And you can see that because x to the 4th, or lambda to the 4th, would have to have 4 zeros, and 0 is the only thing that makes it true, so it's a multiplicity of 4. Lambda 2 is 6, has a single multiplicity, and lambda 3 is negative 2. So there's all of our eigenvalues, and their multiplicities. Here, just for fun, multiplicity of 1, multiplicity of 1. Okay, can you hear the dog snoring? She's snoring pretty good. Okay, let's go balls to the walls here. I didn't mean to say that. I don't know what I'm talking about. We're doing it. We are going crazy here. We are going to go find the characteristic equation, the eigenvalues, and the eigenvectors for this lovely 3x3 matrix. And it's a 3x3 matrix where it's not triangular, right? Not triangular. Now, we can make it triangular, but if I make it triangular, I gotta explain that I made it triangular. That's a whole thing. So what I'm gonna do is, well, first, let's find our a minus lambda I, right? So we'll start there, and I'm gonna write it over here. So my a minus lambda I is equal to 6 minus lambda, negative 2, 0, negative 2, 9 minus lambda, 0, 5, 8, and 3 minus lambda. Now, we need to find the determinant of this, right? So we need the determinant. And we could do the determinant in multiple ways, but it's not a triangular matrix, so we can't just like quickly multiply our diagonals. It's not going to work out for us. So we could get a little weird. Like we could do row operations with our lambda in it, but that's just going to get even weirder. So we might as well do a cofactor thingy or bob. And I'm going to do my cofactor thingy or bob using this row here. And by row, I mean column. And I'm going to do that expansion. That's what I was looking for. So I'm going to do that cofactor expansion using that column because I have 2 zeros in it, which means that I only have to worry about the matrix. I have to worry about this as a multiplier to the determinant of the leftover matrix when I cross out the rest of that. And now if we think about imposing our plus minus, so plus minus plus, it's a positive. So our determinant here, now again, you can find the determinant of this however you like. If you don't want to do the cofactor expansion of that row or that column, find something else. The first time I did this, I just did the cofactor expansion of the top row because I wasn't paying attention and I wasn't thinking about trying to make my life easier. This is going to make my life easier. So the determinant of our A minus lambda I matrix here is 3 minus lambda times the determinant of that leftover matrix, which is 6 minus lambda, 9 minus lambda, minus -2 times -2. Right? And I guess I should not use a square bracket. I should use just a big ass bracket. How's that sound? All right. Unfortunately, we actually need to do some flippity-gibbet here. We need to do some actual multiplying out of these things because we've got some constants here. We've got a single term. We got multiple terms. Do yourself a favor. Let some sort of calculator, computer, something do this actual multiplication and do this simplification out. One way you could do it is if you have a TI-89, you can put it into the expand. You can also go to Wolfram Alpha. And if you do the command expand and then type in this gobbledygook, it'll give you back the polynomial. So it turns out this polynomial comes out to be negative lambda cubed plus 18 lambda squared minus 95 lambda plus 150. And I don't know about you. So there's our characteristic equation. So then we're going to set that equal to 0 as our characteristic equation. So this guy, there's our characteristic equation. And when we factor this, that's going to get us our eigenvalues. Now, pretty sure the last time any of you factored a cubic was probably in, I don't know, 10th, 11th grade, and you probably haven't thought about it since. I'll be honest, I sat down, I did some synthetic division because I was feeling supremely extra. But you do not need to be supremely extra. Go anywhere, I don't care. Go to Desmos, graph it. Go to Wolfram Alpha, ask for it to solve it. Go to Symbolab, ask for it to solve it. I don't care. Find whatever method you need to do to solve this equation and do it. Because it's all about getting the eigenvectors and eigenvalues. I don't actually care about that you can do the algebra to get there. Okay, so that being said, if you go somewhere, I for funsies did actually factor it out, but the eigenvalues I get are 10, 5, and 3. And you'll notice that none of them have any multiples. So none have a multiplicity of higher than 1 because I have this is a 3 by 3. I got 3 eigenvalues, which means I'm going to have 3 distinct eigenvectors. Right? Now, to get the eigenvectors, again, what we're going to do is we're going to set up and we're going to augment. We're going to set up the A minus alpha I times x equals the 0 matrix for each one of our vectors or values, and we're going to augment it, and then we're going to come up with the and we're going to figure out what's left. So here we go. All right, you do it. You set them up, come back, compare, see if you get the same eigenvectors that I do. How'd it go? Did you find the same vectors I did? So again, you would take and substitute your eigenvalue into this vector, augment it with the 0 vector. And when I said vector, the first time I meant matrix. Augment it and then set up your parametric vector form And then the vectors there that are created are your eigenvectors. And they're associated. And now any multiple, again, any multiple of v1 is an eigenvector for this eigenvalue. So if I wanted to get rid of this fraction, another option for v1 would be -7, 14, 11. Right? Those are equivalent vectors in this space because both of those vectors lie on the same line, and it doesn't matter if I take my matrix times any one of those vectors, it's still going to be 10 times that vector. For 5, I got 2 9ths, 1 9th, and again, this is also equivalent to if I multiplied everything by 9, 2, 1, 9, right? Here, the 0, 0, 1, that's nice. It doesn't really matter, all right? All right, so the last thing we're going to talk about real quickly in this section, it's going to come up into play in the next part, has to do with this idea of similarity. Now, we're not going to necessarily or really dive deep into finding similar matrices, but what I want to point out here is this property that says that two matrices are similar if I can find some invertible matrix where if I take that matrix, the inverse of that matrix times my A times that matrix, again, I get B back out. Or if I take A times the matrix times B times, right, then what that's saying is that A and B are called similar. Right? Now, if they are similar, the nice thing that happens is that they have the same characteristic polynomial, so they have the same eigenvalues. Something to be very, very, very cautious of, though, is that notice this did not say if and only if. So I have to know that A and B are similar first. Once I know that A and B are similar, then I can say something about their characteristic polynomials. Just because they have the same characteristic polynomial does not mean that they are similar. So an example of two that have the same characteristic polynomial but are not similar, so 2, 0, 0, 2 and 2, 1, 0, 2, right? These are not similar. Now, I only know that. I just, so think, there's no invertible matrix that I can find that I could multiply each of those by to get me the other, right? So this one actually turns out to be 2 times the identity, which kind of screws things up, but each of these have the characteristic polynomial of 2 minus lambda times 2 minus lambda, right? Or 2 minus lambda squared is our characteristic polynomial in both cases because on this diagonal, the product is 0, right? So they have the same characteristic polynomial. So just showing that they have the same characteristic polynomial doesn't mean that they're similar. But if they are similar, then I know that they're going to have the same characteristic polynomial. So this is a one-way street, guys. And also, similarity is not the same thing as row equivalence. Just throwing that one out there too, right? So these things could be row equivalent, right? I could get 2, 0, 0, 2 out of 2, 1, 0, 2 by doing a row operation. They're equivalent in that way. They're row equivalent, but they're not similar. So they're not similar. Okay, that's it. That's all I have to say about those.